Okay, we're going to talk about projection matrices in this video. I want to disclose that much of this material can be found in Strong's book about linear algebra. Um, yeah, this particular section is pretty nicely explained in his book, so I recommend it. If we have a vector space, well, more specifically, if we have r to the m, so all the vectors with m coordinates, and then we can split this into orthogonal complements. Now, for instance, if we have a dimension 5, just to give an example, if m was 5, we can split this up into orthogonal complements, subspaces, one with dimension 1, the other one with dimension 4. So 1 and 4. Or you can have 2 and 3. Or you can have 3 and 2. Or 4 and 1. And that's about it. We're not going to split this up into, I guess we could. I haven't thought about this more deeply. We could have 0 and then everything else. I have to think about that. But for now, let's think about just 2. So we're going to split this into 2 subspaces. Now, this picture is misleading because when we split into 2 subspaces, there can be more than just those 2 spaces. That is a misleading picture. For instance, if you have r squared, and we split this into this space and that space, so there's the y-axis and the x-axis, those are 2 subspaces. Well, there's a lot of stuff that is not in any of them. So that picture is that is not in one nor the other. So here, when we are splitting this into 2, and there's the 0 vector, 0 is common to both of them. That means that there is more to it. Anyway, so let's concentrate on this. One of the 2 halves. It's not really a half because one could be, especially if we have an odd dimension, one could be of dimension 3 while the other one is dimension 2. And even so, I don't know if the word half makes sense because this line is not necessarily half of the entire plane. It is half in quotation marks in the sense that every other vector is that is not in those subspaces is the addition of one vector from here and one vector from there. There you go. So this is the addition of those 2. So in that case, it is half. Anyway, so let's focus on one subspace. Let's label it C of A for now. And any point here that is not in C of A, but it's in R to the M, can be projected down to a point in C of A. So any element B can be projected into P that is in this particular space. Yeah. And then we can take another point B prime just to differentiate it from B. I guess I could call it B1 and B2, but I'm just calling it B prime. This has nothing to do with derivatives. I'm just calling it B prime. We'll project into this space to another point, say P prime. And then we can have a third B and a fourth B and a fifth B. We can have many Bs. So the way to mass produce those projections, an efficient way to mass produce those projections is to find the projection matrix corresponding to this subspace of R to the M. Yeah. So Mr. Strong in section 4.2, he comes up with a very nice formula for a projection matrix. So if A is made up um, in columns by a basis of this subspace, then, and I'm going to come back to that in a moment, but I don't want to lose the formula. The formula will be A times the transpose of A times A again, the inverse of that times the transpose of A. Boy. Okay, so again, what is our goal? Among other things, one of the main goals is to come up with projections into a subspace of a big space. So you take an element and you project. An element, project. And I'm going to talk more about the projections in a moment. But I just want to give you the big idea of what's going on right now. So we want to project, mass project elements into this one space. Now, projecting only one might not require this because there's a lot of computations going on here. There's a lot going on here. So doing this is a lot of work. It may not be worth to do all of that for only one element. But if we're going to mass project a bunch of elements, then this, especially if this space is really not very easy to visualize, then coming up with a matrix will make things way easier, way simpler. It's a little bit like this matrix reminds me a little bit in concept to the quadratic formula. You know, if you're going to solve one quadratic equation, which you can factor easily, then using the quadratic formula is excessive. It's too much work. You know, the negative b plus minus the b squared and all that, and then there is a possibility of making a mistake when we square the b on where we subtract the negative 4 bc and then divide by 2a. I always make the mistake. Well, I shouldn't say always, but I frequently make the mistake when I'm applying the quadratic formula to multiply 2 times a. I always put the 2 and I forget the a, for instance. So why should we do that when we can simply factor a polynomial, if we could factor it, and then we get the answer much faster, much easier, and with less risk of making a mistake. So this is kind of like that. There's a lot going on. We have to multiply, you know, have a matrix, multiply with the transpose, then we have to find the inverse, which is already a chore, and then we got to multiply again and multiply one more time. That's a lot of work, and there is a lot of room for mistakes when performing this computation, so be aware of that. Why would we want to do it? Because then once we have that projection matrix, we can project very quickly, very easily, very systematically, points after points after points. Now, if we change the space to another space, then we have to come up with its own projection matrix. Yeah. So that is the idea of what's going on with projection matrices. But let me explain a little more what projection matrix, what a projection in general is. So if you have a line, just any line. So let's talk about projections. Okay. So if we have a line and we have a point anywhere outside the line, and so pretend this is the floor, and then there is a speck of dust somewhere in the air, and the sun is directly above the floor, 90 degrees perpendicular. Now, something that I studied in cosmology was that this, well, and this is pretty well-known knowledge. The sun is much bigger than Earth, and consequently, the rays of light can be thought of as parallel on Earth. So all the rays of light can be thought of as going down this way. Yeah. That's why, you know, you remember in basic algebra, you know, Yeah, the classic problem that you have a tree, and then you got a person, and the tree casts a shadow of so much, and then uh, the person has another shadow, and what is the height of the tree based on and of course this is an easy proportion problem, but it's based on the fact that the rays of light coming from the sun are parallel. So this line is parallel to this. So that is the same sort of example. So this speck of dust is going to produce a shadow, a tiny little shadow. Where is it going to be? We're assuming that the sun is perfectly vertical above us. So, or above the floor. Where will that be? Well, that's going to project down here. And if we have this dotted line, then we can think of this as 90-degree angle. So this point down here is what we call the projection of this B point onto this line. So that is the projection. Notice that this distance is the shortest distance from B to the floor. Any other distance you take is going to be longer because it is going to be a hypotenuse with this as one of the legs. So the shortest distance is going to be this leg. So that is the projection on the floor. Nice, good. All right. Projecting on the floor is easy. Let's label this as example 1. Example, that's not an example. I'm going to do example 2 here. Let's pretend you have the whole floor. So the difference between example 1 and example 2 is that we're projecting onto a line in example 1, and now we're going to project onto a plane. So again, pretend we are on the floor, or this is the floor. The sun is coming down perfectly above the floor. There is some object, small object, flowing above the floor somewhere, and the light is going to produce, well, the blocking of the light by this is going to produce a shadow. The shadow will be perfectly below this point. Let's call this point, whoops, not P, B. P is the projection. That's what we call the projection. So let's call it B, and then P will be the projection point on the plane. Yeah. If the problem is easy enough, then these projections do not require much of a formula at all. So let's actually be more concrete. Let's say we have r squared. So that is all of our plane, r squared. And then we got a point here. So 3, 1. Yeah, I just made that up. So projecting this onto this line will be this point. And what are the coordinates of that point, by the way? 3, 0. So projecting into the x-axis, super easy. Just erase the second coordinate and voila, we're done. Projecting onto the y-axis, which is the other, well, there's many subspaces. So this is a subspace, that is a subspace. Any line through the origin is a subspace. So this is B, this is the projection onto this line. And then projecting onto this line is super duper easy. It is gonna be, if you have to guess, you're probably thinking this, 0, 1. So just delete whatever the other component is, and then you're all set. Now, mind that projecting onto a different line, say this one, will mean finding the point so that is closest to this line on this, finding the point on the line that is closest to the 3, 1. So that would be somewhere in here. that's not so easy to figure. And pretend this is y equals x line. That's a good problem we're going to solve. We're going to come back to this. So 3, 1, project into that. And you can probably use some geometry, some trigonometry perhaps, because the angles are going to be 45 degrees. So we're probably going to have some kind of square root of 2/2 going on. But the point is, what if it was y equals 2x or y, we can have any kind of slope. We can have a line going this way or down here. How do we find in a systematic way the projection? Now, each line, each subspace will have its own matrix. We're going to focus on finding that matrix, so that when we multiply the matrix with 3, 1, we are going to obtain this point automatically. Now, mind, doing those two is not too hard. Something that is not perfectly on the x-axis or the y-axis will be more difficult. Example 4. Let's say we are in 3 dimensions. So this is an r cubed. And let's do 3, 1, 2, 3, 1, and then 5. So 3, 1, and then 5. So we're going to be 3, 1, 5. Okay, so somewhere around here. 3, 1, 5. So we go 3 this way. Well, let's do this. Go 3 this way, 1 this way. So this is 1, 3 across, or down this way, 1 across, 5 units up, and that takes us to 3, 1, 5. Okay, what is the projection of that point? And we're going to label that as B. What is the projection of that point down to here? Well, that's easy. It is 3, 1, 0. So just wipe off the 5. Let this drop on the floor. Essentially, that's what it is. That's another analogy, I suppose. I didn't think of that. Take that point that is up in the air, pretend there's gravity going down, let it go, and it's going to perfectly go down to this point. When it hits the floor, that's the projection. But then we can project onto that plane. So pretend the gravity is going in that direction, away from us, and hold that for a moment in that place, let it go, and then if you let it go, it's going to go straight to that wall. Okay, so the projection on this wall would be so 0, 1, 5. So this point would be 0, 1, 5. Take the point again, lift it up, and now pretend the gravity is going this way. Boy, this makes me think of that book. What's Ender's Game? And forgive me for not knowing the author. I should know the name of the author. Ender's Game, the book, because he's there in space, and then they have to change the gravity, and Ender is really good at figuring out gravity. Anyway, and again, forgive me for not knowing the author of the book. But anyway, pretend gravity is going in to our left, and then you take that object, hold it, let it go. So when it drops in quotation marks because it drops towards the gravity or the pulling of the gravity, it's going to go in this direction, and it's going to hit the wall here. And so we're going to go 3, 0, 5, and that's going to be the coordinates 3, 0, 5. Normally, those are the projections. Those are I would call standard projections onto the XY plane. So we're projecting onto the XY plane or the YZ plane or the XZ plane. And those projections are not difficult at all to understand. You know, if we project into the XY plane, get rid of the Z. Projecting into the YZ plane, get rid of the X. Projecting into the XZ plane, get rid of the Y. Everything seems to work nicely. But here's the twist. Um, let me come back to this and just now. We don't need a lot of formulas to do this. This is pretty straightforward, but here's the twist. What if the plane is some kind of a weird plane going, this way across, and behind that, and it comes this way, and it's just tilted in a weird, it's got to go through the origin because we have to have a subspace. So this plane is nice and flat, horizontal. That plane is vertical, plane vertical. Everything is nice and square. But this guy, would be kind of, pretend that's behind, this line is behind. So pretend there's an angle, a weird angle coming this way, but another angle coming the other way. Now, finding the projection of this point onto this plane is not going to be, so let me kind of draw a picture over here. So pretend the plane is there, and then the point is somewhere in here. So projecting means pretend gravity is behind the plane, and the plane goes forever. So pretend gravity is behind the plane, and then we let it go. Where is it going to hit the floor? Pretend that's the floor, but the floor is all tilted. Well, it's not obvious. It's not going to be here because that's not where gravity is pulling. It's pulling directly behind the plane. So it's maybe here. Whatever shortest distance it is, that's where it's going to go. Man, so that is not easy. That's where this formula for the matrix will be very, very handy, very useful. Okay. So I haven't described, other than multiplication of matrices and inverses and transpose, I haven't told you what the matrix has anything to do with the plane. Oh, by the way, we can do this with 4 dimensions. However, it is harder to visualize. 5. So can we have a 4-dimensional space? Sure. And to be honest, up to last night, I was very, very hesitant, extremely hesitant to draw any picture. I'm in my 50s. I'm older. And for all these years, for all these decades, I've been very hesitant to draw any picture that has dimension greater than 3. I just stay away from it. I just don't do it. But until last night, I thought, wait a minute, maybe we can think of the 4th dimension being vertical, and then the other 3 as the plane, the floor. So there is the 4th dimension, and think of the other 3, even though a plane is really only 2-dimensional, there is the X and the Y. But so think of this as R cubed. This plane, even though it doesn't make sense because a plane should be 2-dimensional. So it doesn't make sense to have R cubed. But for purposes of analyzing projection, it makes sense to think R4 in this context. So pretend we can collapse somehow all of R cubed, which is a space, a 3-dimensional space, into a plane. There it is. So for instance, this point on this 3-dimensional space could be 3, 1, 5, 0. 3, 1, 5, 0. 0 because it doesn't go off into the 4th dimension. So it is only using 3 dimensions. It is a 4-dimensional point though, mind, but it is not off. Kind of like a point, where's my, here, a point here, there, this point here is in 2 dimensions, but yet it is on the one-dimensional space. It is not off into the second dimension. So perhaps this is an interesting way to draw pictures in 4 dimensions. And so a point up here, say 3, 1, 5, 2, is 2 units directly above. Notice that I'm using quotation marks when I say above. By above, I mean in the positive direction of this 4th dimension axis. So if this is 2 units above this, then the projection of this point is back into here. Isn't that cool? So for purposes of projection, perhaps we can describe a 4 dimensions as a plane with an additional, a 3-dimensional plane, whatever that means, in addition to the 4th dimension. I think this is not a bad idea. That is not a bad idea. Because what I thought about last night is, well, what is the distance between those 2 points? There's a formula for the distance, and it doesn't take too much to realize, well, if that's the same, and those second coordinates are the same, and the third coordinates are the same, then the distance has to be 2. So for projection purposes, we can think of a 3-dimensional space as a flat surface, just a flat surface, for purposes of projection. Anyway, let's go through some actual examples. So projecting, let me just recap a little bit here. Projecting onto XY plane, you know, the standard planes, YZ plane, XZ plane, no problem. Projecting into something that is not horizontal or vertical, and even if it was vertical, projecting into a vertical plane that is not those two, I don't think is trivial. I don't think it's easy. By the way, we can possibly use calculus to do that. We might need multivariable calculus, I think, and but we can probably do that with calculus because we can minimize the distance. We're not going to do that, of course, but and we can do that as a standard problem in calculus. You know, if you have a line, oh yeah, here, you know, like finding the closest point on this line to 3, 1, that is a standard calculus problem. So you find the distance, the generic distance to an XY point here, and then you find the derivative of the distance, and then you set it equal to 0 using Fermat's theorem, and then I'm pausing because now I'm beginning to forget whether it is Fermat's theorem or not. Anyway, and then find the critical number, and then you know the drill, the optimization problem in calculus 1. But let's do some actual problems. So, oh, there's one other thing I need to tell you. So this subspace has to be described. How do we describe the subspace with a basis? That is very important. One of the most efficient ways to describe a subspace is with a basis. So the matrix A will be a basis of that subspace. So the columns of A must be a basis of the subspace we project onto. Okay. All right, so let's do a problem, a more concrete problem. I'm gonna piggyback on this. So example 3, I'm gonna use example 3. Yeah, but I'm gonna make a new problem out of it. So 5, 6, example 6. Okay, so in R squared, find projection matrix P onto the line y equals x, period. Okay, so that is exactly the problem we had. There is the line y equals x, and I want to be able to project, among other things, 3, 1. So pretend 3, 1 is here. And I want to find a matrix that projects this point onto the line perfectly on a 45-degree, rather on a 90-degree angle. So this distance is the shortest one, absolutely. But then the advantage of figuring out that a matrix is that if we take any other point, we will be able to project very swiftly, very nicely, very well onto this line. Okay, so let's follow the formula. Oh, the formula calls for a matrix A. A has to have columns that generate this line. This line is a subspace of R squared. Okay, so what generates that? Well, we can simply, because this is a 45-degree angle, we can simply use 1, 1. If you use 2, 2, that should be okay. So let A be 1, 1. Okay. Let's apply the formula. So the formula for P calls for, let's see the first page of today's video. It is here. P equals A transpose of A again, close parenthesis, inverse, and then the transpose of A. And I checked earlier all the dimensions, the size of the matrix should work. So A is a single matrix. That one. Okay. So we're going to figure out the transpose. So the transpose is, of course, this matrix horizontally. By the way, by habit, I'm writing this horizontally, but it should be a vertical vector, 3, 1, just like that one. Anyway, so A is, well, no, the transpose, let's do this. So the transpose of A is 1, 1. Of course, A is 1, 1. So the transpose multiplied with A is 1, 1, 1, 1. And you know how to do that. It's a 1 by 2 matrix multiplied by a 2 by 1 matrix, giving us a 1 by 1 matrix. So that's going to give us, which is the same thing as a regular number. I think I have mentioned that it wasn't earlier. And I probably have to make a short video of why I think I changed my mind about one by one matrices not being real numbers. Anyway, let's do the product. So 1 plus 1 is 2. That's a 1 by 1 matrix, by the way. Okay. So I'm still thinking about that 1 by 1 business. Anyway, so that is this. Oh, but then the inverse. What is the inverse of that? Well, it's got to be another matrix that multiplied with this matrix gives us the identity. And the identity is 1. So I have to have 1/2. So this guy has to be 1/2, the inverse. So A transpose A inverse will be half, well, the matrix 1/2. So this is a 1 by 1 matrix. And then multiply by A on the left. Yep. So A times A transpose A inverse is, so A is, remember, 1, 1. But then we're going to multiply by the 1 by 1 matrix. This is 2 by 1 multiplied with a, oh, this is almost too small. 1/2. This is a 1 by 1 matrix, a 2 by 1 matrix. So we do, the result of that is going to be a 2 by 1 matrix. So we do 1 times 1/2. So that's going to give us 1/2 and 1/2. And then we multiply by the transpose. Okay. So P, that's our final step. I was doing this step by step. So those two first, inverse, so that was the 2. The inverse is the 1/2. And then multiply with that, that's here. So all of this is this matrix, but now we're gonna multiply by the transpose. So, and that's gonna be our projection matrix P. So P will be 1/2, 1/2. We can probably factor out the 1/2, but I'm gonna leave it alone. And then times the matrix 1, 1, the transpose of this matrix. Okay, this is 2 by 1, this is 1 by 2, so we're gonna end up with a 2 by 2 matrix. So 1/2, 1/2, boy, it's just 1/2 everywhere. 1/2 and 1/2. Or the other way to put it, factor out the scalar 1/2, and then we have 1, 1, 1, 1. Okay, so that is our projection matrix. If we multiply 3, 1 by this, or if we multiply this with 3, 1, we will be able to project onto this line. Let's see if that is true. So P times 3, 1, many times we label this as B, little b, B as in boy. Well, that is 1, 1, 1, 1. Oh, I missed the 1/2 in front because that is a scalar. And then 3, 1. So let's keep the 1/2 there. Oftentimes when we have a fraction, a denominator, we factor it out so that we end up with nice whole numbers inside the matrix. So 3 plus 1 is 4. 3 plus 1 is 4. But then we can multiply through and we end up with 2, 2. Oh my goodness, 2, 2 is the projection of this point onto, perfectly, onto this line. 2, 2. That is the closest point on the line to this point. You know, out of curiosity, I'm thinking, you know, we should always be a little skeptical. Always, always, always. Please be skeptical. That's a good thing to be. I mean, reasonably skeptical. That means I believe you, but let me double check. I think you have good intentions. I think you're trying to tell me the truth, but let me double check. I think that's a healthy attitude in all the sciences. So let's use a little bit of calculus very quickly. That shouldn't take long at all, just to recall. Okay, so pretend you got a point, a generic point x, y on this line. Now, because x is equal to y, that point is really x, x. So the distance between 3, 1 and xx is, well, d equals, and you guys know the distance is x minus 3 squared plus 1 minus x squared. So I'm using calculus. This class Um, this is about linear algebra and not necessarily calculus, although functions belong to a vector space. And so we could perhaps use some calculus. In fact, the solutions to differential equations, many of them are subspaces of the space of functions. So yeah, we can interrelate a little bit, but this is more of a calc 1 kind of thing. Anyway, so the derivative, um, so 2 times the root x minus 3 squared plus 1 minus x. Well, I meant x minus 1, but it doesn't make much of a difference here. And then by the chain rule, we have to multiply by the derivative of those. So 2 times x minus 3 plus 2 times x minus 1. But the 2's simplify, we can factor the 2, cancel. So and then we want to set equal to 0, set equal to 0. So we end up with x minus 3 plus x minus 1 equal to 0. Yep, x minus 3 plus x minus 1 equal to 0, because we assume the denominator is not 0, so we can multiply. And we end up with 2x minus 4 equal to 0. So sure enough, x equals 2. And because x equals y, y equals 2. And technically speaking, we should do some kind of a test to verify that we are getting the minimum. So let me skip the test of minimum. I'm going to write that down, though. Skipping, verifying minimum. Okay, so, but I just wanted to check, and sure enough, the answer is 2. The answer we got from multiplying this matrix with this fellow, with this point, will give us the closest one, which is, in my opinion, amazing. I mean, we don't have to do calculus. I did the calculus just to double check, and it does work. This is amazing. So 2 is the shortest distance, or the point with the shortest distance between a point on the line here and 3,1. Now, if you change the point, how about a point farther away, like 5,0 on the x-axis? Yeah, so let's label that as example 6b. Yeah. Well, we found the matrix, by the way. The question is, find projection matrix P onto the line y equals x. We got to pay close attention to what the question is. The matrix is this one. There's the projection matrix. So this was just done to analyze what happens if we have a point. Let's take another point. Another point. Say, what is it? 5,0, the one I was describing here. So if we are farther away, 5,0, let me draw a new picture. 45-degree line, 5,0. What is the point that is closest to 5,0 on this line, on the line y equals x? No problem. We already have the matrix. The matrix is a half, 1, 1, 1, 1, multiplied with 5,0. So that is 5, 0. So that's 5. And then 5, 0, another 5. But then we gotta multiply by a half. So we get 5 halves, or 2.5. I'm going to use decimals. I usually don't use decimals, but when we have nice decimals such as 2.5, I just use them. So if you go half the way up, yeah, half the way up, that's 2.5. That point, 2.5, comma, 2.5, is the one that is closest to this guy. Yeah, which makes sense because then we have an isosceles triangle. Wait, but how do I know that this is a 90-degree angle? Well, it is. It does work. Anyway, we can verify it using some kind of geometry or trigonometry, simple trigonometry, but it does work. Now, if we tilt the line, so let's say you have the line, so example 7, new example. Find P, and by P we mean the projection matrix in R squared that projects onto the line y equals 2x. Okay, so now we got a new problem. The line is steeper. Yeah, it's 1-2 kind of ratio. So the question is, let's start with the same point we had early. And this is a sub-example. They're not asking for the actual projection. But let's say this is 3-1. 3-1. And I want to project onto this line. So we want to find the point on the line that is close. So this angle has to be 90 degrees perfectly. And we want to find this point. So because this angle is more than 45 degrees, and we want this to be perpendicular, so this angle kind of goes like that. See, in this picture, we have 45 degrees one way, 45 degrees the other way. But if we change the angle, then that's going to turn. So this is a little less vertical or more horizontal than here. We want to know where this point is. Well, we can use calculus. We can even use geometry. I have seen students using basic algebra, because what they do, some students say, oh, well, the slope here has to be 2. The slope of the reciprocal line has to be -1/2. And they find the equation of this line, and they know the equation of this line, and then they do the intersection, which is more like algebra 1 or algebra 2 or college algebra, pre-calculus for sure, and then they find the point. But let's do it with linear algebra using matrices. So A, in this case, is going to be the single, remember, A is the one that produces this guy. So we need one point on the line. And so if the slope is 2, I did have it here, y equals 2. Then what is one point in it? So if x is 1, that's easy to figure. If x is 1, then y is 2. 1, 2. There you go. So that is an element, a point on this line. And then we can do our steps. So let's quickly go through them. So the formula calls for the transpose times A. So A transpose times A is 1, 2 times 1, 2. And that's going to give us 5. But then we're going to do the inverse. So, well, that's going to give us 1/5, which is going to be really a scalar. The 1/5 can be pulled out. So we need to multiply with A again and the transpose. So P is 1/5, the scalar coming from that, because we got to do the inverse of that matrix. And then times A times the transpose. So A is 1, 2, and the transpose is 1, 2. But now we have a 2 by 1 and a 1 by 2. So we're going to end up with a 2 by 2 matrix multiplying with 1/5. So 1/5, 1, 2, 2, 4. Bingo, we got the matrix. Boy, that wasn't at all painful. So this is P. If the question asks, what is P? Find P. Well, there we have it. P is this guy. Yeah. And you can multiply the 1/5 through, and then we end up with 1/5, 2/5, 2/5, 4/5. But So that is the end of the problem. But now I'm curious. I want to know where 3, 1 goes to when we project onto that line. This is really, really, really cool, I think. So 1/5, 1, 2, 2, 4, multiplied with 3, 1. Keep the 1/5. So 3 plus 2, 5. So let me do that again. 3 plus 2 is 5, because that is going to cancel with the 5 nicely. 6 plus 4, 10. Oh my goodness. I did not realize that 1, 2, that, believe me, that is pure coincidence. I wasn't even planning on that. So 1, 2, the point we picked, that was a pure coincidence. I just said x equal 1, and that caused y to be 2 because 1 is an easy number to pick. By the way, it is a good idea for you to convince yourself that if you had you picked another number, say 3, 3, 6, 3, 6, the matrix will be the same matrix. It wouldn't change even if we pick 3, 6, 3, 6. So it's not a bad idea for us to check that, to go to the site and think, oh, he just said that if I put 3 and 6, this matrix will be the same. I do want to believe him, but I'm going to double check. That's what I call a healthy amount of skepticism. When you say, you know, he means well, he must be right, but it doesn't seem. Why don't I check? And go ahead and check. And please tell me if I'm wrong. Yeah, 1, 2. So that is the closest one. And then we can mass produce projections. If you take any point, a random point on the plane, 5, 0, you know, what is the projection? That would be a neat one to check. I'm not going to check it because I want to move on to another example. Okay, so x7, 7, example 8. Okay, we want to move on. Example 8. Okay, so now let's say you have 3 dimensions. So now we're in R cubed. And we have a single line. Where do you want the line to go? On the XY plane, or, you know, just somewhere in the air? Let's start with something with a line that is kind of known. You know, the line y equals x on the plane. So this line is on the XY plane, and it goes this way. And it is, all the x's are equal to the y on those points, but the z value is 0. So there's no lift to this line. This line is on the floor. So a generic point on this line is x, x, 0. Okay. So the question is, what is the, and then what is the matrix that projects onto this line? See, that gets a little weirder. Let's say you have 3, 1, 5. So remember that point 3, 1, 5? How do we project this onto this line? So remember, this line is somewhere. So if you rotate and look at a different angle, the line will be on the floor. The point is going to be floating above, not above, directly above it, notice, because this point is not. So let's say this is 3, 1, 5. So that point is not above it. If it was above it, it would be 3, 3, and then 5, for instance, but it is not above. So it is at an angle. So this point is not directly above the line. It is off. But then still there is a point that is closest, and that is the projection we want to find. So there's going to be, so this line continues to the back here, and there's a point. And actually, I can Yeah, it's got to be here in the front, but I don't know where it will be. Can we use calculus for that? Yeah, yeah, I believe so. Oh, yeah, definitely. Yeah, because we had X. We can use calculus 1 to do that. Um, but we're not going to use calculus this time. We're just going to find the matrix. So find P. Now, each object that we are projecting onto has its own P. What we need is one vector, one non-zero vector on this line. So, and it's easy to pick 1, 1, 0, 1, 1, 0. Because if X is 1, then we have 1 and then 1 and 0. Okay. So our matrix A is going to be 1, 1, 0. And then remember, it's the only problem with starting out with this formula is that if we use it, then perhaps we lose track of where the formula came about, which has a lot of value, the understanding. But so there are two parts to this mathematics. One is applying a formula that is reasonably complicated like this one, although the more we do it, the less complicated it seems, and then figuring out where it came from. At this point, we are just applying the formula and see what we get. So the formula has parentheses here, and so I'm going by PEMDAS, parentheses first. So the transpose with A. So we're going to do 1, 1, 0. Well, I'm going to do it in our head. This is 1, 1, 0 times, horizontally times vertically. So that is really the dot product between this and itself. So we're going to end up with 1 plus 1, 2. And then the reciprocal of that is going to be a half. So by inspection, without doing too much, we know that the product, this is, including the inverse, is going to be a half. So the last thing we have to do to figure out P is, so keep the 1/2. We're going to multiply A with the transpose. So we're going to multiply 1, 1, 0 with its transpose, 1, 1, 0. And that's going to give us a 3 by 3 matrix multiplied with 1/2. So that's 1, 1, 0. Again, and then 0, 0, 0. So there's our projection matrix. Man, that is fast. So if we want to project any point onto here, so the answer is here. Projection matrix is there. That's it. We're done finding the projection matrix. If we want to project this point onto this line, in other words, now again, pretend you rotate this and you're looking from this point of view, and you can even tilt it. So this is the picture we end up with. What is this point? So pretend you have a point and gravity is pulling towards this line. There you go. That's another way to put it. And you drop it. But again, gravity is sideways gravity. It's not straight down gravity. It's sideways towards the line. You let it go. Where is it going to hit the line? Well, let's do it. I'm kind of excited about this. I need more paper. So another page. So we got, so this is capital P. The projection which we were going to label little p is a half, 1, 1, 0, 1, 1, 0, 0, 0, 0 times 3, 1, 5. And that's going to be a half of 3, 4, 3, 4. Oh, that's perfect. Oh, it is 2, 2, 0. Interesting. Oh, I guess if we look at the picture from the top, the picture looks exactly like this. If this point is 3, 1, 5, and we're looking from the top, we don't see the 5 because the 5 is towards us. So it does make sense that we end up with 2, 2, 0 as before. Okay, that's kind of neat. Okay, but many problems are not going to be this nice. So pretend now we have some kind of some line that is not nice 45-degree angle with respect to the x and the y axis. So example, I have to look back because I forget what number we're in. 9 next. Example 9. Let's say we have some line, let's say, kind of going this way, but with some kind of height. So um, mm, 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 there. So a line that goes like this. So let's say this is 1 unit. I don't want to use 3, but let's say 4. So this is not really well scaled, but that's all right. And let's use 2. So 1 this way, 4 this way, and then 2 up. And there's the line. So this vector, the direction of this line is 1, 4, 2. So this point is 1, 4, 2. That's that's one vector that can generate this line. Now mind, any non-zero vector on this line will generate the line. So if you take twice as much, yeah, 2, 8, 4, which would be twice as much, that point will also generate this line. And this line keeps going on the left too. Okay, so let's look at 3, 1, 5. So 3, 1, 5 is going to be somewhere really far away. So here, 3, 1, 5. And we want to find the projection onto, boy, I would be really weird if the projection was by coincidence 1, 4, 2. It shouldn't be. But the projection that goes right into there somewhere. So again, pretend this line is horizontal, pretend this point is, even if you have to rotate, but you get it directly above it, pretend gravity is behind the line. So this is going to drop to the line. Where is it going to drop? So again, we're changing gravity. It's like putting a magnet right behind the line, but a super long magnet. So it's going to go to the closest point. I think gravity works better than magnet, but anyway. So the question is, where is it going to, what is the projection of this point onto this line? That is the question, the projection. So that is the 90-degree angle straight down to the line. Now, down is whatever the line is. Okay. So let's do the matrix. Let's find the matrix. So I'm not writing the question because this is exploratory. We want to find the matrix. Pay attention to what the question is. It could be find the matrix or find the projection. The matrix corresponding to this one, 3, 1, 5. So what is A? A is this guy. So we're going to do the dot product, because really that's what it is. If we do A transpose with A and we have a 3x1 matrix, we're really just doing the dot product. So that's going to be 1 and 16, 17, and 4, 21. So the dot product is 21 of this with itself. Let me double check. 1 and 4, well, 1 and 16 is 17, and 4, 21. Yep. But then we're going to do the inverse of that, 1 over 21. So P is going to be 1 over 21 times 142 vertically and 142 horizontally. Okay. So we're going to end up with 1 over 21, 142, 4, 16, 8, 2, 8, 4. There, this is our projection matrix. Man, this is nice. This is easy. I mean, see, as the line gets more complicated, like with an angle, it gets much more complicated to use calculus. And this gets not more complicated. Although it is going to get a little more complicated, but by a little bit in the next example. Okay. So let's project the point. So 1 over 21 times 1, 4, 2, 4, 16, 8, 2, 8, 4. Let's project the point 3, 1, 5 and see where on the line it will be when we project. So keep the 1/2 there. And we're going to multiply that last. So that's 3, 17. Double check. 3, 17, 12, 28, 68, 6, 14, 34. Please tell me if I did anything wrong. 34, double that is 68, double 17. So we can factor out the 17. So this is really 17 over 21. So that's a weird fraction, but the direction is going to be 1, 4, 2, which makes perfect sense because that is the direction of this vector, 1, 4, 2. Now, 17 over 21 is a proper fraction. I just want to have an idea of what it is. 17 over 21 equals about 80%. So I just divided 17 over 21 and I got 0.8. So that is about 80% of this vector. Think about that, 1, 4, 2. So if this is the vector 1, 4, 2, shrink it down to 80% of what it is. An approximation, by the way. The actual answer is 17 over 21, 68 over 21, and 34 over 21. Those are the precise, perfect coordinates of the point where this projects onto. So this point will project right about here. And the precise coordinates, again, are going to be 17 over 21, 68 over 21, there's 1, and then 34 over 21. Those are the precise coordinates of this guy. In fact, I'm going to write them down. 17 over 21, 68 over 21, and 34 over 21. Those are the precise coordinates of this point. If we do this factor in and then we do the actual calculation, it's about 80% of this. And that gives us an idea of where it is relative to this point. If this is the origin and that's the point 142, 80% is about this much. So that's the projection of this point onto this line. All right, so now let's change the problem. Okay, because we've been projecting on lines, so we're experts on projecting points on lines. What about projecting onto planes? Okay, so 10. Let's say we have a plane. Consider the plane x plus 2y plus 3z equal to 0. It has to go through the origin, so we have to have 0. Okay. Find the matrix that projects into that plane. So, 1, 2, 3. Let's see, that plane, if I'm not mistaken, so 1, 2, 3, it's got to be perpendicular Man, it's going to be hard to draw, but the back of it is going to go like so, and then there's going to be some, and then it's going to go under. So this is an approximation of how the plane, it goes through the origin, by the way. Um, yeah, so maybe this line should be behind this. Anyway, so that is a rough approximation of this plane. And let's say we have the point, to be consistent, let's say we have the point, you know what point I'm going to use, 3, 1, 5. And we're going to drop that point into the plane. But we're not going to, if gravity was pulling our normal down, on the floor, it will go down here somewhere on the plane, and it will hit the plane there. But we're changing gravity. We're assuming that gravity is behind the plane, or the plane is gravity. Oh, that's different because this extends this way. And so when it drops, it's going to drop somewhere in here. I think behind this octant, somewhere back there. So the question is, where is it going to drop? If on this plane, if the gravity is pulling towards the plane, this plane, not this plane. Whoa, that's not an easy problem. Can we use calculus? Yes, but then it gets more complicated because now we need two variable calculus, calculus 3, not regular calculus, differential calculus. We need multivariable calculus to start working that out. Yeah, it gets complicated. However, with matrices, it is going to be a little complicated. I cannot lie to you. It's going to be still a little complicated, but it's going to be, in a way, simpler. Okay. So here's the first challenge. We have to find a basis for this plane, a basis, something that will, a vector that is on the plane. So randomly, sort of randomly, pick an x value, say, but an easy one, such as 1, and a y value, 0. Pick 1, 0. So we're picking those two. And then if this is 1 and this is 0, that will force z to be something, what would it be? So 1 plus 3z is equal to 0. Move the 1 over. I'm not putting this because we're assuming, so we're picking two numbers, two easy numbers, 1 and 0. Don't pick 0, 0 because then you're just going to get the origin. And we want non-zero vectors. So 1, 0, and then another, what number will make it work? Well, z, in order for this to work, has to be negative 1/3. Negative 1/3. I'm going to avoid, so if you go 1, 0, in order to stay on the plane, you have to go down by 1/3. So this, yes, this is in front, and this line is on the back. Yeah, that makes more sense to me because this line is also on the back. This is on the front, and then that's on the back. Okay. But then the question is, oh, what I was going to say is, so that point would be somewhere down here. So 1, 0, then down. So 1, 0 down. So pretend that point is on the plane. Oops, I meant on the plane. Anyway, I prefer not to use fractions. And so if we multiply by 3, we're still going to be on the plane because the plane through the origin is going to be a subspace and it has to be closed under scalar multiplication. So multiply by 3 and we get another point on the plane. It's going to be a little farther away, yes, but what do I gain? No fractions. So multiply by 3 to obtain 3, 0, negative 1. Okay, so that point is on this plane. I need another point that is on the plane that is going to be not on this line. And the plane is two-dimensional, so we need two vectors to produce this plane. And at random, I'm going to pick um, 0, 1 this time. 0 and 1. So we have to figure out what z value will make that work. So if this is 0 and that is 1, that means that we have a 2. 2 times 1 is 2. And so when we solve for z, move that over to the other side. So that is -2 divided by 3, so -2/3. Yep. And then multiply by 3 again. Multiply by, so semicolon, by 3 to obtain 0, 3, -1. And those two are linearly independent because they're not a multiple of the other. One is not a multiple of the other. Okay, so we got two vectors. Interesting. We got two vectors. So the matrix A, wait, back up. Two vectors that generate this plane. Two vectors that generate this plane. So our matrix A is made up by the columns of the matrix A are going to be those two vectors. So A will be, now I thought, what order should I use? And I don't think it matters. It shouldn't matter. So let's do 3, 0, -1 as a column, 0, 3, -1 as another column. Okay, so that's our matrix. And then we're going to go back and do this computation. Transpose times A. So these are not column vectors as in the previous example. So the multiplication is going to be not just the dot product. It is going to be a little more complicated than the dot product, but it's not going to be too complicated. So now I got to be a little more careful. Let's figure out this product first because it's not so easy. It's just a little bit more complicated, but not a lot. And the inverse is also going to bring another complication. Let's do that. So transpose A. So this is A transpose A. I'm going to do this in steps. So that is A. Transpose is going to be 3, 0, -1 across 0, 3, -1. And then we're going to multiply with A itself, 3 across 0, 0, 3, -1, -1. Okay, so let's see what we get. We get 9, 10. 0, 0, 1, 0, 0, 1, 0, 9, 10. Nice, we get a nice square matrix, of which we're going to find the inverse. So remember, we're developing P. Here's the formula for P. I'm going to box it. And I'm going on parentheses first because I'm using PEMDAS, parentheses, multiplication, and so forth. So we already multiplied those two. Here they are. Now we're going to find its inverse. Okay, so I'm going to use the Gauss-Jordan elimination. See, in the previous examples, this was just a number, like 5. So the inverse is 1/5, no problem. But this is a matrix, so we got to figure out what the inverse is. Let's see. So the Gauss-Jordan elimination, 10, 1, 1, 10. Oh, I meant to put the unit matrix on the side. Yeah. So 1001. So this is a new thing. We're applying the Gauss-Jordan elimination process to figure out the inverse. So do R1 minus 10 times R2. So 10 minus 10, 0. Whoa, 1 minus 100. negative 99. Okay. 1, negative 10, and then keep the other guy alone as is. 1, 10, 0, 1. We're going to switch those two. So R1, switch it with R2, and we're going to end up with 1, 10, 01, 0, negative 99, 1, negative 10. Ay, ay, ay. So we can divide by 1, we can divide by negative 99, the second row. Negative 1 over 99, second row. And we end up with 1, 10, 0, 1. Yep. 0, 1. Negative 1 over 99. Where did that negative? Oh, yeah. And negative, well, that's going to be positive 10 over 99. Okay. So then we subtract from the second row, no, from the first row, the second row, 10 times the second row. So take the first row and take away 10 times the second row. So of course we got 1, 0. We're going to take away 10 times this guy. So that's 1 over 99. We're going to take away 100 over 99 from 1. So I believe that's going to give us negative 1 over 99. Oh, and then we're going to end up with 0, 1, negative 1 over 99, and 10 over 99. There's a problem here because this, I think this is not quite right. What did we do to go from here to here? We subtracted 10 times, so I missed the 10. There's the 10. Yeah. Okay. So based on that, and we can factor out the 1 over 99. So according to that, A transpose A inverse is equal to 1 over 99. So factor out the 1 over 99, 10, negative 1, negative 1, 10. Okay. So apparently that is our inverse. You know, I want to double check. What was the original matrix? Negative 1, 10. So that is the one that we claim is the inverse, and the original matrix is 10, 1, 1, 10. Well, let's see. So we have 10 or 100 minus 1, 99. 10 minus 10, 0. Negative 10 plus 10, 0. Negative 1 plus 100, 99. Yeah, that works because that did not include the division by 99. So those would have been one. Yeah, if we put 1 over 99 here, then we would put 99 there. And that will give us the identity. So we're good. This is the inverse. Yeah, with all the steps, I would hate to make a mistake that I don't catch soon enough. My philosophy is not to avoid mistakes, although we do avoid them. I'm not saying that just lightly. My philosophy is anticipate some mistakes, and then so that you still give yourself time to fix them. Okay, so next I'm going to multiply A with the matrix we just, so again, I'm following this recipe. This is a recipe. Do those and you're going to get your, do this and you're going to get your projection. So next, we want to multiply with A, this guy by A times A transpose A to the negative 1. What was A? There it is. A is 3003 negative 1 negative 1, and we're going to multiply with 10 negative 1 negative 1 10, and there's an extra 1 over 99 in front of that. Okay, so let's figure this out. So that's going to be 1 over 99, keep it out, and then we have 30 and negative 3 and negative 3 again, and 30, and boy, that's going to be, so negative 10 plus 1, negative 10 plus 1, negative 9, 1 minus 10, negative 9 again. You know, we can factor a 3 out of the entire thing. So that's 3 over 99. And then we have 10, negative 1, negative 1, 10, negative 3, negative 3. When there's more negatives than positives, what I do is I factor out the negatives, so there are fewer negatives than positives. So, and as long as we're doing that, of course, we're going to simplify this. So that is negative 1 over 33. So we factor out the negatives. That's not necessary, though. Negative 10, positive 1, negative 10, positive 3, and positive 3. So now we got only 2 negatives as opposed to 4 negatives. But that's me. You don't have to do that, I think. Okay, so one more step to get to our, so is it more work? Yes, because we have to think about it. We have to come up with the 2 vectors that generate the plane. That was already some work. On top of that, so then we could make the matrix. The multiplication is more work. The inverse, more work. And then we still have to keep multiplying with things. So the projection matrix, capital P, is negative 1 over 33 times negative 10, 1, 1, negative 10, 3, 3. Boy, I should have, I'm just going to do this in the next page. There's no room here. So the projection matrix P is negative 1 over 33, 10, 1, 1, negative 10, 3, 3. And then we multiply with the transpose of A. The transpose of A is 3, 0, negative 1. Wait, yep, 3, 0, negative 1, 0, 3, negative 1. So this is a 3 by 2, 2 by 3. We're going to end up with a 3 by 3 matrix, a nice square matrix. And negative 1 over 33, 30, 3, negative 10, minus 1, negative 10, Let me check something. -10, -10. I remember two -10s. Good thing I'm catching that right now. -10, 1, 1, -10, 3, 3, 3, 1. Yep. So I gotta fix this a little bit. -30. Yeah, that should be -30. 3, 10 minus 1. Okay, that's just the first row of the product. 3, -30, -1 plus 10, 9, 9, -6. And we can factor out 3 again. So we end up with -1/11. And we multiply with 10, rather -10, 3, come on, 1, because we are dividing by 3, 3, 1, -10, 3, 3, 3, -2. Isn't that neat? That is our P, our projection matrix. What do we gain by that? If we want to project our point, remember our point? So this is P. This is one part of this talk. If we want to project our point, and what was our point? Our point was, remember in this problem, example 10, we want to project 315 onto this plane. Where will it hit? Well, let's see. 315. So if we have -1/11, 10, rather -10, 1, 3, 1, -10, 3, 3, 3, -2, which by the way, it is a nice 315 symmetric symmetric matrix. Let's say -30, -29, -14. Let me double check. -30 plus 1 is -29, plus 15 is -14. 3 minus 10 is -7. 8, 9, 10. You gotta be kidding. 9, oh, 12. Yeah, that's another 3. So 9 plus 3 is 12, minus 10, 2. Okay, so the point, the precise point where, if we drop 315 onto this inclined plane, where gravity is pulling towards the plane, we're gonna get the projection. So this is little p. The projection will be double negative. So 14/11, 14/11, 8/11, and 2/11. Oh, but those are going to be negative. -8 and -2, because we're multiplying by -1/11. So a little bit towards us, left and down. Boy, that was 4 pages, but my writing is big too. But So when we drop this a little bit towards us, left and a little down, yeah, so that means that this is going to drop. Oh, that's reasonably close. It is not 3-1. Oh, my guess is that it is because, so it's kind of down here, kind of behind and below. Yeah, because there's an incline, this inclines this way also. Yeah. Yeah. So that point, oh, wait a minute. This is not vertical. This is supposed to go, see, if I do it, my picture of the plane is incorrect. It's not accurate because if I do it perpendicular how it's supposed to be, it's going to be, it doesn't seem to match the point. So either I made a mistake here, which I could have, or my plane is not very well written. But there's something we should check regardless. Now that I think about it, there is something we have to check. The projection has to be on the plane. It's going to drop this object. So never mind, because I was thinking straight down. It doesn't go straight down. It has to go on an angle. But that means that this plane is incorrectly drawn. The angles are not quite right. But what I should verify is that this projection is actually on the plane. It has to be on the, because it projects onto the plane. So I'm going to check what happens if we have, remember, this is x value, y value, z value. So 1x, 14/11, plus 2y's, -8/11, plus 3z's, -2/11. And where am I getting those? So 1x plus 2y's plus 3z's, I'm getting that from the original problem. The original problem says you got a plane, x plus 2y plus 3z, x plus 2y plus 3z. I don't know if it's 0. It better be 0, otherwise that point that we found does not belong to the plane, which means we don't have a projection. So let's figure this out. So all the denominators are 11. We can put everything under 11. So we got 14 minus 16 plus 6. Yep, there's a mistake because, oh, that's supposed to be a negative. So that is not 0. And that means this point does not belong to the plane. 14 minus 16, 2 times 8 is 16, minus 6. No, that's not 0. Whatever it is not 0. So okay, I found a mistake and I'm super duper embarrassed because it happened way, way at the beginning. And you probably saw the mistake. This is example 10. Here, way at the beginning, we have a -2/3 multiplying by 3. I got all hung up with this -1, and I didn't realize this guy should be -2. Yep, array. So that has a chain effect. Who knows? I might put that into as the one of the questions on the next assessment to fix the problem and provide the correct a projection matrix and then the correct projection. And I knew once I got to here, there was a mistake because the point, the projection point has to be on the plane. And it isn't. When we add those numbers together, we don't end up with 0, and we're supposed to end up with 0. So then I came back and looked at this and I realized, oh my goodness, I can't believe this happen? So please fix the mistake. Who knows, that might be a question. And then we'll stop the video here. Thank you, guys.